This is the video introduction to Activity 3.2, Introduction to Quadratic Functions. In this activity, we'll analyze quadratic extended tile sequences and use black and red squares when modeling these sequences. We'll learn to distinguish quadratic extended tile sequences from linear extended tile sequences. We'll learn to graph quadratic functions and note key features on the graphs, such as turning points, x-intercepts, and y-intercepts, and we'll connect these ideas to the ranges of the quadratic functions. And we'll learn to use technology to support t-table and graphing work. The materials we'll use are black and red tiles, white and opposite white X strips, and some new pieces, black and red X squares. The black X square represents a positive square output number, x squared, which can take on the values of 1 squared, 2 squared, 3 squared, etc., or any real number squared, such as 2.1 squared. Both edges of the square are the same length as the long edge of the white or opposite white X strips. Because the square is black, the dimensions of the square can be x times x or minus x times minus x, and the value of the square is always positive. A red square represents a negative square output number, negative x squared, which can take on the values of negative 1 squared, negative 2 squared, negative 3 squared, etc. Both edges of the square are the same length as the long edges of the white and opposite white X strips. Because the square is red, the dimensions of the square can either be x times negative x or negative x times x, and the value of the square is always negative. Here are some pictures of the dimensions for the black X square. You can see on the left we have x times x is x squared, and on the right we have negative x times negative x is x squared. Here are the dimensions of the red squares. On the left we have negative x times x is negative x squared, and on the right we have x times negative x is negative x squared. Either one works. How do we model with these black and red X squares? An extended sequence of tile figures whose X figure is modeled by a black X square might look like the following extended sequence of tile figures. You can see that each tile figure is a square array of tiles. The Figure 1 is a 1 by 1 array, Figure 2 is a 2 by 2 array, Figure 3 is a 3 by 3 array. And when you look at negative 1, figure negative 1, it's a negative 1 times a negative 1 array to have it be black, and figure negative 2 is a negative 2 times a negative 2 array of black tiles. In a similar way, we can model a sequence that would be all red squares and would be modeled with a red X square. Note the usefulness of the dimensions of the tile figures. Rather than marking the individual tile counts, it's easier to notice that the dimensions follow the figure number times the figure number pattern for the black tile figures, and the figure number times the negative figure number, or negative figure number times the figure number, either works, pattern for the red tile figures. You can use similar ideas to evaluate the square components of tile figures. When you sketch black and red X squares with or without edge pieces, you may simply sketch the square outline and mark it with an x squared or negative x squared. And when you sketch the edge pieces, you can sketch a line and mark them with either x or negative x units. As we continue modeling extended tile sequences in Chapter 3, the importance of matching the dimensions, the edge lengths, will be really important. So you can see you can sketch a black tile x square, and you can sketch a red x square. We'll also need some function terms in this activity. A polynomial of degree n is a function p of x of the following form, and notice that an, the first number, can't be 0. In this polynomial, the coefficients are the real number factors of each term, so a0 through an, and the powers of the variable terms, so 1 through n here, are positive counting numbers. The degree of the polynomial is the largest power on x, and the leading coefficient is the coefficient of the term of the polynomial with the highest power. A parabola is the graph of a quadratic function, and a quadratic function is a polynomial of degree 2. A quadratic function has a turning point, which is either the lowest or the highest point on the graph of the parabola. Here are some technology tips. To facilitate your work with functions with real number coefficients, you might find it useful to use technology to create t-tables for a given function and to display, inspect, and move function graphs. There are free online graphing calculators. There's a variety of them, apps and websites that you can employ. For example, one easy-to-use online calculator is Desmos, desmos.com, which you can easily view a graph and a function t-table at one time. There are many quick Desmos tutorials available online. Simply search for Desmos and a topic. For example, search for Desmos with equations and tables. If you have a graphing calculator, they also have a built-in t-table feature. Search for your calculator name and table, for example, TI-84 function table, to find tutorial videos for your specific calculator.